In our previous lecture we were discussing about the momentum integral equation for boundary layer in presence of zero pressure gradient, and we came up with this form of the expression, and the whole objective of doing the analysis was to calculate the wall shear stress. Now if you look into this expression, you will see that you may calculate the wall shear stress provided you know what is the velocity profile within the boundary layer, because that is what is an unknown in the integral expression which is there. The big question is that what should be the velocity profile. Any velocity profile which you may choose or approximate in general will not be the correct one, because the correct one should come out of a detailed solution of the flow field and then what is exactly there within the boundary layer. But you may always substitute this velocity profile with some approximate velocity profile which sort of satisfies your boundary conditions. So when it satisfies your boundary conditions and the velocity profile is substituted here, our expectation will be that the velocity profile may be inaccurate, but in a somewhat integral form the velocity profile should give not a bad estimate of the wall shear stress. And this expectation is from the fact that after all the boundary layer is very thin, so error in the velocity profile may be important when you consider the velocity profile as such, but in the integral sense the integral of the velocity profile might not be that erroneous. So that is one of the expectations. So whether that expectation is justified or not, the best way in which we may look into it by some example. So let us say that we want to have a polynomial approximation of the velocity profile. So for example, one may have different forms of this expression, like one may assume a polynomial like this, even you may consider a fourth order term, and that is what was done by an engineer known as Pohalhusen. So his particular method was dedicated in the name of his honor, but here we are not going for a fourth order polynomial. We will leave that on you as an exercise in your assignment problem, but we will consider a third order polynomial. Even one may consider a first order polynomial, one may consider a sinusoidal function. So many different forms of the functions are possible. Within the constraints of the function you have to satisfy the most important boundary conditions, so that these unknown constants a0, a1, a2, a3 whatever, these are determined. So let us look into this special case as an example problem and see that how do you calculate the boundary layer thickness, the wall shear stress and the total drag force on the plate on the basis of this. So to do that, first of all we have to understand that how do we calculate these coefficients. So if you have 4 coefficients, you must satisfy 4 boundary conditions to get these 4 coefficients. Let us see what are the most essential boundary conditions that you need to satisfy. What is the physical problem we are considering? You have a flat plate on which you have a free stream flow coming with a velocity u infinity, and the boundary layer is growing like this, and you are interested in describing a velocity profile at a section, some section x. So what are the boundary conditions that you want to satisfy? Boundary conditions. What is the most essential boundary condition that you would always like to satisfy? See, the boundary conditions should come in order of priority, because if you choose lower order polynomials you may not be able to satisfy all the boundary conditions because you have less number of coefficients, but the most essential one you should always satisfy. What is the most essential one? No slip boundary condition at the wall. So u equal to 0 at y equal to 0. Then what happens in the outer stream? So let us say that y equal to delta. Y equal to delta in an engineering sense is equivalent to y tends to infinity in a mathematical sense, because outside delta whatever happens is like far stream. Okay. So literally it is the variable y by delta or eta tends to infinity, but it is as good as y equal to delta. So at y equal to delta, what are the boundary conditions? Okay, u equal to u infinity at y equal to delta. Any other boundary condition at y equal to delta? So u does not change further with y at that means the gradient of u with respect to y equal to 0 at y equal to delta. A fourth boundary condition, of course you may go on adding here, like in terms of a boundary condition at y equal to delta, you may also have the second order derivative of u is equal to 0, but more important boundary condition which has a priority over this is what happens at the wall, because at the wall you have one boundary condition, but if you really have a liberty to put more, the priority should come there, because these two are quite sufficient to describe what happens at the boundary layer, but this alone is not very sufficient to describe what happens at the wall. I mean, if there are scopes of incorporating more boundary conditions at the wall, it would be better. So look at the governing equation. Let us try to satisfy the governing equation at the wall. See, this velocity profile does not understand the momentum equation, right? It is just an approximate velocity profile. So we will try to teach the velocity profile in such a way that it's in a way satisfies the constraints of the governing equation at the wall. So at the wall, if you look at the boundary governing equation, so if you have let us write the momentum equation, the boundary layer equation basically. This is the boundary layer equation. When you consider flow over a flat plate, essentially it is a zero pressure gradient. So this term is not there. Let us try to satisfy this at the wall. At the wall, u is equal to 0, right, by no slip boundary condition. At the wall, v is equal to 0 by no penetration boundary condition. That means you must have the second derivative of u with respect to y 0 at the wall, right, which follows from the governing equation. So this is not a boundary condition that you directly find out intuitively, but if you want to make sure that the momentum conservation is satisfied, then that is what you get. So the remaining work is easy, that you substitute these 4 conditions, so you will get 4 algebraic equations involving a0, a1, a2 and a3. So from that you find out a0, a1, a2, a3. So I am not going into the details of the algebra because it is too trivial. So at the end what you will get out of this is u by u infinity is equal to 3 by 2 y by delta minus half y by delta whole cube. So the remaining terms will go away. Okay. Now at least once you get out of this whether your algebra is correct or not, at least you should check that it satisfies most of the essential boundary conditions, that at y equal to 0 u equal to 0 and at y equal to delta u is u infinity. Now what we will do with this velocity profile? We will use this velocity profile for evaluating the integral which is there in the expression. So to do that we will write tau wall by rho u infinity square is equal to d dx of integral 0 to delta. Now we will write 3 by 2 y by delta minus half y by delta whole cube into 1 minus 3 by 2 y by delta plus half dy. With a obvious substitution of variable, that is eta equal to y by delta, you may write this as tau wall by rho u infinity square is equal to d dx of integral 0 to 1 then 3 by 2 eta minus half eta cube into 1 minus 3 by 2 eta plus half eta cube d eta, and then multiplied with a parameter delta, because dy is equal to delta into d eta. Okay. So, change of variable is there. So, important thing is, see, first of all this delta is dependent on x, but this integral evaluation is not dependent on delta. So, you can take this delta out of the integral. So, it boils down to evaluating some sort of an polynomial expression and then coming to the integral. Again, let us not waste any time in like doing this very simple algebra and simple integration. Let us say that out of the integration what you will get? You will get a number, say you get a number k, which comes out of the integral of this entire expression. It is a definite integral, so it will come like a number. Now, what is the tau wall? Tau wall is mu into this one at y equal to 0. So, that also you may calculate from your assumed velocity profile. So, what is your assumed velocity profile? So, that is this one, and you may calculate the first order derivative at y equal to 0. So, that will be 3 by 2 delta, because remaining term will have y which will be 0 at y equal to 0. So, you will have mu into 3 by 2 delta, rho u infinity square is also there in the denominator, is equal to k into d delta dx. Okay. So, then you can integrate this, and once you integrate this you will get delta as a function of x. So, let us write the integration. So, you have delta d delta is equal to mu by rho u infinity square to 3 by 2 k dx, right. So, if you integrate it, delta square by 2 is equal to 3 by 2 k mu by rho u infinity square x plus constant of integration. As we know that in the limit as x tends to 0, you have delta tends to 0, that is the edge of the plate where from the boundary layer grows, and therefore you must have c equal to 0. So, you see the growth of the boundary layer is like an initial value problem, where you start with x equal to 0, and whatever condition is at x equal to 0, all the subsequent conditions for delta may be evaluated. So, the x coordinate here acts like a time coordinate, as if you have started with time equal to 0, instead of time equal to 0 it is x equal to 0, and as you march along x in the positive direction, you see that the boundary layer grows. So, this is called as a marching problem. So, instead of marching with respect to time, you are really marching with respect to space or position. So, now you can find out what is delta by x. So, delta square will be 3 by k. We will always write mu by rho as nu, because kinematic viscosity is what that governs the physical situation. So, nu by u infinity square x. So, you can see clearly that delta varies with square root of x, which we have also seen from the previous analysis, like the order of magnitude analysis and the Blasius solution. Now, if you want to find out how delta by x is scaled, so basically what you have to do, you have to divide by x square. So, if you divide it by x square, then okay, one important thing is we have missed one u infinity here, because this u should be, I mean it is u into u infinity is this one. So, somewhere u infinity has to be there. So, yes, 2 by yes into u infinity. that is one u infinity we have missed. So this u infinity and this u infinity will cancel, so eventually we will have only one u infinity here, right. So for evaluation of the tau wall there was one u infinity here. So this is u infinity, that has to be there. Now if you divide it by x, so delta by x square is 3 by k into nu by u infinity x, that means delta by x is square root of 3 by k into Reynolds number to the power minus half. Okay. So if this is calculated, this comes out to be this particular number, roughly, if I remember correctly, roughly 4.64. So see, this is somewhat erroneous, because if you remember the Blasius solution, this was 5. So instead of 5 it is coming out to be 4.6 or something like that, but the important thing is that the scaling behavior is similar. See, the order of magnitude gave delta by x of the order of Reynolds number to the power minus half. The exact solution is like 5 into Reynolds number to the power minus half. Some approximation it is deviated from the exact solution, but we are not really that much bothered about this one. This is somewhat disturbing because the approximate solution is somewhat deviated from the exact one, but this is what is not our focus. Our focus is the wall shear stress calculation. We are never expecting that it will give the correct boundary layer growth, but our expectation is that at least the integral of the velocity profile will nullify the error in the velocity profile to some extent and get a better estimation of the wall shear stress. So let us calculate the wall shear stress. So if you write the wall shear stress tau wall, that is mu 3 mu u infinity by 2 delta, that is what, and delta you may substitute as a function of x. So delta is nothing but 3 mu by 2, 3 mu u infinity by, in place of delta we will write square root of 3 by k into square root of nu by u infinity x, right. So what we will get essentially say tau wall, what is our matter of interest is the non-dimensional form of the tau wall. So the non-dimensional form of the tau wall is given by this Cf, which is the friction coefficient, which is tau wall by half rho u infinity square. So you divide this by half rho u infinity square. So one of the u infinities get cancelled, then you are left with, there is one mu by rho, that means it is basically something into which one, this x is no, just I am using this expression. So delta is square root of this one whatever into square root of x, okay. So that is what is substituted here. So this one something into nu by u infinity into root over nu x by u infinity. So that means Cf is coming out to be something into Reynolds number to the power minus half. See, this becomes square root of u infinity, this numerator becomes square root of nu. So square root of nu by u infinity x, right. So this constant, if it is evaluated, this comes out to be 0.646, okay, and the exact solution, the Blasius solution, gives this one as 0.664, and this is really quite close. So the error between these two may not be that significant for a calculation, for an engineering calculation, and therefore you see that remarkably, although the velocity profile was erroneous, although the boundary layer thickness was quite erroneous, this is also erroneous, but the error has somewhat gone down, and that is because of using this in the integral form. So the whole expectation is that the functions may be inaccurate, but area under the function as area under the curve, that may be the approximately the same despite the error in the functions themselves. So this sometimes is called as skin friction coefficient. So sometimes this is given with a subscript x. So Cf with subscript x for Cf as a function of x, and the name of this is known as skin friction drag coefficient. Why it is so? Because we will later on see that there may be other mechanisms of having a drag force on a body. So here this drag force is originated out of the frictional action or the viscous action. So this is given a name of skin friction drag coefficient. The subscript x to indicate that it is local friction coefficient, that means as you change x, this will vary. Now one is interested at the end to calculate the total drag force on the plate. So how do you calculate the total drag force on the plate? To calculate the total drag force on the plate, basically you have to keep in mind that the wall shear stress varies locally with x, and it is important to take care of that local variation. So to take care of that local variation, what we may consider is, say let us say at a distance x, we take a small strip on the plate of thickness dx. So the plate is having some width, so it is basically there is a strip which has some width. So let us say that the width of the plate is b. So the element that we have considered is something like this, and the shaded portion which is there, this is where it is exposed to the fluid, and that is where there is a shear stress between the fluid and the solid. So how do you calculate that what is the total shear force on this element, whatever is the shaded element? So let us say that dF is the shear force on the element. So what is dF? So tau wall is the wall shear stress, that into B into dx, okay. So if you want to find out the total one, of course you have to integrate it. So the total F, so let us give it a subscript d to indicate it is a drag force. So Fd will be integral of tau wall b dx from x equal to 0 to x equal to L, where you know that how tau wall varies with x. So that is already known to us. So tau Fd, let us write integral 0 to L, in place of this one we will write 3 by 2 mu by square root of 3 by k u infinity divided by nu by u infinity x into b into dx. So again, if you consider the form like there will be some numbers based on what is the value of k, then mu u infinity divided by square root of nu by u infinity b, then just integral of x to the power minus half dx. So, it will become this one. Now, just like the local skin friction coefficient is a non-dimensional representation of the wall shear stress locally, there is also a non-dimensional representation of the drag force, and that is given by coefficient of drag. So, let us write what is the coefficient of drag. So, the coefficient of drag is given by Fd divided by something reference. See, this is a force. So, this should be represented by some equivalent half rho u infinity square, that is there, times some reference area. So, what area you will choose here? So, if L is the length of the plate, B into L. We will see later on that depending on the shape of the body, there are engineering conventions of what reference area should be taken. So, this fundamentally is like some reference area. For flow over a flat plate, it is like this B into L, but for different shaped bodies, we will see if it just flow past a circular cylinder, maybe flow past a aerofoil section, how these reference areas will change from one to the other. It is nothing very fundamental, it is an engineering convention that what reference area you choose for designating the coefficient of drag. Now, here you can write it in like you will get some number times mu u infinity by square root of nu by u infinity, then you get rho u infinity square into, you will get a square root of L, because numerator square root of L, denominator is L. So, again you will get one of the u infinities gets cancelled out. So, this is something into Reynolds number to the power minus half, but Reynolds number is based on L. So, this Reynolds number is not based on any local coordinate, but the total length of the plate. So, this gives the total effect, and this coefficient is just double of this 0.646. So, it is whatever like 0.646 into 2. And it is therefore also quite close to the result that one gets from the exact solution or the Blasius solution. So, what we get out of this exercise is, we have seen that how by using an approximate velocity profile we may estimate how the boundary layer thickness grows with x, how we calculate the wall shear stress, and how we calculate the total drag force and their non-dimensional versions. Again, because this is originating out of a skin friction force, so sometimes this is given with a subscript CDF. So, F for skin friction, because as I have mentioned, we will encounter such examples where there will be also other mechanisms of the drag force, not just the wall shear stress. Okay.